Hello everyone. In this video, we are going to solve some examples related to polar coordinate system. Let's look at these examples. In this figure, the platform is rotating at any instance with this theta. As you can see, the theta is given as a function of the times, okay, and the ball rolls outward and the position of the balls at any instance is follow these equations. We should find the magnitude of the velocity and acceleration of the ball when the time is at 1.5 seconds. As you can see, all the informations we have for these problems is related to theta and r. For this reason, for solving these problems, we will use the polar coordinate system. This is all the information that we have. The theta is given. Okay, the theta is given as a function of the time and follow these equations. And also the position of the ball at any instance is given as a function of the time. We should, at time 1.5 seconds, we have to find the velocity and accelerations. This is the equation of the velocity and acceleration in the polar coordinate system. For the velocity vector in polar is follow this equation, r dot er plus r theta dot e theta. And acceleration follow this equation, r double dot minus r theta dot square. This is for r component or radial components of acceleration, and r theta double dot is represent the alpha plus 2r dot theta dot, and the theta dot is show the omega. This is the whole, the components of the theta or transverse component for accelerations. As you can see, for velocity and acceleration, based on these two equations, we need to know that the value of the r dot, r double dot, theta dot, and theta double dot. For this reason, we should find first and the second derivative for theta and r. Then we can find these value at time 1.5 seconds and add together. For finding the r dot and r double dot, we have this equation. The r as a 0.1 t cube as a meter. The r dot is a derivative of r respect to the time and is 0.3 t squared as a meter per second, and r double dot is a second derivative of r respect to the time or derivative of r dot respect to the time. If I take a derivative from this equation, I have 0.6 times t. This is meter per second squared. And this is for theta. For finding the theta dot that represent the omega, we should take a derivative from these equations, and the value is 6t to the 1/2 radian per second, and alpha is a derivative of omega respect to the time, or second derivative of the theta with respect to the time. And also we show for theta double dot. Once we take a derivative from this equation, the answer is 3 times t to the negative 1.5 radian per second squared. For finding the velocity and accelerations, okay, we should to know that the value of these 6 components at time 1.5 seconds. At time 1.5 second, the value of the R will be 0.3375 meter. The R dot equal 0.3 times 1.5 squared, just plug to the equation. And this is the answer, 675 meter per second. And R double dot, or acceleration, or it's better just R double dot, is 0.9 meter per second squared. And again, I found all of these data or information just by plugging 1.5 seconds in these 3 equations. How about the theta, omega and alpha at time 1.5 second? Just we plug this value to these 3 equations. The value of the theta is 7.248 radian. Theta dot is 7.348. Okay, now we have already found all of these these 6 data value. Now we are plugging to the equation of the velocity and acceleration. Velocity at time 1.5 second is R dot ER or theta dot E theta. The value of the R dot is 0.675 ER. The value of the R is 0.3375. And this is the theta dot. This is the vector of the velocity. As you can see, for polar coordinate system, the velocity in general has a 2 component, radial component and transfer or theta components. But if you remember in previous video, for normal and tangential coordinate system, the velocity just has a 1 component along the t-axis or along the tangential components. This is about the velocity in polar coordinate system. And this is the magnitude. Is 2.57 meter per second. This is the value of the velocity at time 1.5 seconds. For finding the accelerations, have this equation of double dot square ER E theta. Now we are plugging all the information that we found in this part of the problem. We have 0.9 minus this is about radial component of accelerations, and for transverse or theta components we have 7.348. This is for E theta. This is the answer of these, the whole of these quantities, and the value of these quantities is 10.75 E theta. This is the vector of the acceleration in polar coordinate system, and the magnitude of the acceleration is find by this equation. Is 20.4 meter per second squared. This is the answer of the question 1. Let's look at the next examples. Okay, for these problems, rotation of the arm about point O is defined by theta, and the theta is given as a function of the times. And the color B sliding along the arm, but these equations, as you can see, the position of the color B along this rod is follow these equations, and this is about the positions. After the arm has rotated through 30 degrees, determine the total velocity of the color and the total acceleration of the color. For these problems, we have information about the theta and r, and also and now we have to find the velocity and accelerations once the arm is rotated 30 degrees. Okay, and now we have to find these components. Okay, this is the theta. This is the position, t squared. And this is the point O. This is the rod, and this is the color. And the theta is increased in this way. The first step, we should set up the polar coordinate. We should know that how to set up each component of the polar system. For the radial component, always start from origin, reach the object, and we continue. Okay, and this is as a positive direction for radial components. Outward from origins, okay, is always as a positive direction, and this is about the negative area for radial components. The angles is increasing in this way. For this reason, the theta or transverse components, okay, is perpendicular to the radial components, is meaning the R, and toward to the increasing the angles, okay, become as a positive direction for theta components. And this is about the negative area for theta. The points for the polar coordinate system, the positive direction. First, the radial component should start from origin, reach to the object, and continue. And outward from the origin, always as a positive direction for radial component. How about the positive direction for the theta components? It depends on which directions the theta is increasing. Maybe the theta increasing in this way, or maybe increasing in this way. Depends on the direction of increasing. The positive direction for theta will be determined. Okay. This is the information that we have about the theta and R, and at theta as a 30 degree, we should find the velocity and acceleration. What is the equation for velocity and acceleration at polar coordinate system? The V as a R dot ER and acceleration follow this equation. As you can see, for finding velocity and acceleration, we need R dot, R double dot, R dot, R double dot, theta dot, and theta double dot, okay? For this reason, we should find the derivative of the first and the second derivative of the theta and R, okay? And we should know that what is the value of this component once the theta has a 30 degree. Okay, but look at the problem. These two equation is given as a function of the time, okay? And we can find the time based on these informations. We evaluate the time for theta as a 30 degree. The first step, the 30 degree should convert to the radians, okay? For this reason, we multiply to the pi over 180 and become 1 pi 6. This meaning 30 degree is a pi over 6 radian. If we assume the pi as a 3.40, we can say this is approximately as a 0.524 radian. Okay, now we plug this value to the equation of the theta. And once we solve the equation at time 1.869 second, the collar or the rod is rotated 30 degrees. Now we can find the value of the velocity and acceleration at time 1.869. This is the R. This is the first derivative of the R or R dot. And the value at time 1.896. And R double dot is minus 0.24 meter per second square. This is the value of the R. And for the theta, alpha, and omega, we should take a derivative from the theta. The value at time 1.896 would be 4 radian. Okay, now we on all of these 6 data that we need for velocity and acceleration. For velocity, we are using these equations, and once we plug it to the equation of the velocity, we have minus 0.449 ER plus 481.561. This is as a E theta. This is the vector of the velocity, and the value of the velocity or magnitude of the velocity is 424 meter per second. And the next one is the acceleration. For acceleration at time 1.896. Just plug the information that we found in the previous step and plug it in the equation of the accelerations for polar coordinate system. Okay, 1.61 E theta. Mean the whole of this bracket has a theta component of accelerations. The answer of these problems is minus 0.3091 ER 359 E theta. This is the vector of the accelerations, and the magnitude of the acceleration is 1.31 meter per second square. Let's look at the next example. Okay. At the instant shown, the r as a 3 meter and the theta 30 degree. The Cartesian component of the velocity at point A is given as a 2 meter per second along x component and 8 meter per second along the y component. Determine the velocity of point A in terms of polar coordinates, and for part B, what is the angular velocity of the theta, angular velocity or omega of the crane at the instant shown? It's meaning the first step, for the answer of the part A, we should convert all the informations from Cartesian coordinate system to the polar coordinate system. And for part B, we should find the omega. Let's look at the solution of these examples. This is all the information that we have. The R 3 meter, the theta 30 degree, the velocity along the x component, and y component is given. This is the point A, okay, and the value of the R is 3 meter. The first step, this is about x and y. The first step, we should set up the polar coordinate system. As we know that for setup of the radial component, the radial component start from origin, reach to the object, and we continue. Outward from the origin become as a positive direction for the radial components. Okay, this is the positive direction for radials. And if we continue these lines, this is about negative area for radial components. If the object is rotated in this way, we can say this is the positive direction for theta, and the theta component is perpendicular to the radial components. Okay, and this is the positive directions for theta component, and this is the negative direction for radial component, and for the theta components. The information that we have, the theta is 30 degrees. Okay, this is the location of the object. Also, we have information about the velocity along the x component, that is 2 meter and 8 meter per second for the y component, and both of them in a positive direction. For solving these problems, there are many solutions, okay, but this is my solutions, okay. I resolve these two vectors along the polar coordinate system. First, I start with resolving the velocity for the x component along the r and theta components. If I resolve it this and this vector, this is one component, and this is another component of the velocity. Again, this is the vector of the velocity for the x component. Now we are resolving along the r and theta. We learned that before the angles next to the angles always as a cosine. Okay, for this reason, this component is show 2 cosine 30 and this one as a 2 sine 30. If I write the vector of the 2 meter per second, resolve it along x and y, along the r and theta, as you can see, for the radial component is in the positive direction. For this reason, we have 2 cosine 30 ER. And how about the radial? This is for radial component. How about the theta component? Is a 2 sine 30. But how about the directions? This is the positive direction for theta component, and this is as a negative. For this vector, for this component is located in the negative direction of the theta. For this reason, is a negative 2 sine 30 e theta. Exactly we do for the next vector, is meaning the velocity along the y components. This is 30, this one is 60, this is 30. Okay, now we are resolving these vectors along the r and theta. This is one component and this is another component of this vector. This is 8 cosine 30 and this is 8 sine 30. Okay, and as you can see, both of them is located in the positive direction for r and theta. We have 8 cosine 30 at the e theta plus 8 sine 30 er. Now we are at the theta component together and r component together to find the velocity at point A. This is theta component and this is about the radial component. The velocity at A, at point A, will be 5.73 as the radial component and 5.93 e theta as a theta component. This is the vector of the velocity. This is the answer of the part A. For part B, we should find the angular velocity of the object, omega, or d theta dt. If we look at the equation of the velocity for polar coordinate system, we have r dot er or theta dot e theta. It's meaning for finding the omega, we should use the theta, the information for the theta component of the velocity. The theta component for these problems, say v theta is a r theta dot. For this problem, v theta is a 5.93. And how about the r? The The R for these problems is 3 meters. The distance from origin to the point A, okay, is 3 theta dot. And once we solve this equation, the theta dot or omega or d theta over dt will be 5.93 over 3 or 1.98 radian per second. This is the answer of these questions. Look at this image. A boat is searching for underwater archaeological sites in the Aegean Sea moves at 2.06 meter per second. This means the total velocity of the boat is 2.06 meter per second and follows the path by this equation. And the theta is as a radians. Let's set theta as a 2 pi radians determines the boat's velocity in terms of polar coordinate system and in terms of Cartesian coordinate system. For these problems, just we are focusing how to find based on the polar coordinate system. This means we are skip this and the Cartesian part. The total velocity is 2.06 meter per second. The R at a 10 times theta. Once the theta has a 2 pi radians, find the velocity in the polar coordinate system. The velocity in polar coordinate system follow this equation. R dot ER or theta dot V theta. As you can see, the path is R equal 10 theta. For this reason, for the velocity, we have radial component, we have dr dt or r dot, okay, is defined by derivative of the 10 theta dt that become meter per second. This is about the radial components, okay? And we don't know what is the exact value, okay? And the only things that we have is the total velocity is 2.06, okay? Now at theta as a 2 pi, we can say the R as a 10 to pi or 62.8 meter. Okay, and this is about the equation of the velocity in the polar coordinate system is a VR squared plus V theta squared. What is the radial components? Is a R dot square. This is R theta dot square. This is the value of the velocity, 2.06 to the power 2. And how about the r dot? The r dot is 10 times d theta dt. And how about this part of the component of the velocity, meaning the theta component is r. The value of the r at theta as a 2 pi is 62.8 square times theta dot square. Theta dot is mean derivative of the theta respect to the time to the power 2. 100 d theta dt square, 62.8 square, and now we can find the value of d theta over dt or omega based on these informations. Okay, again, 2.06 as a total velocity of the boats. And once we solve these equations, the value of the dt over d theta over dt or omega will be 0.0323 radian per second. Now we find all of the components, okay, for the velocity in polar coordinate system, r dot and r theta. Once we plug this information to the equation of the velocity, we have 10 r dot, okay, is the 10 times dt over d theta over dt, that is this value. And this is about the theta dot. And once we put together the value of the radial component on 32, 323 ER plus 2.03 E theta. This is the vector of the velocity or velocity in the polar coordinate system. And once the positions of the boats, okay, as a 2 pi. Look at the last examples for this topic. Okay. For these problems, the coordination of the color A is given as a 2.3 and 1.9 feet along X and Y respectively. The color is sliding on the bar from B toward to the C at a constant speed of 4 feet per second. What is the velocity of the color in terms of polar coordinates? And for part B, use the answer of the part A to determine the angular velocity of the radial line from the origin to the color A at the instant shown. Okay. Next, this is all the information that we have. Okay, this is the color A that is moving along this rod from B toward to the C, and this is 60 degree, and the velocity of the color A is given as a 4 feet per second. At the location of the color A, okay, from origin is given, okay. The X component is 2.3 feet and the Y component is 1.9. We should find the velocity in polar coordinate system and also find the theta. Okay. The first step for solving these problems, okay, we should set up the polar coordinate system. As I mentioned in the previous examples, for the radial components, always start from origin, reach to the object, and continue. This is the radial components. Okay, most common mistakes between the students for this type of the problems start to set up the radial components from this point to here. Okay, it's meaning they set up the radial component in this direction, but it's totally wrong. Always the radial component start from origin, reach to the object, and continue. How about the theta component? And this is as a positive direction, and that side as a negative direction. How about the theta? If the rod is rotated in this way, the positive direction for the theta will be here, perpendicular to the radial components. Okay, and this is the positive directions for theta, and this is the negative direction for theta. This is the first step for setup of the R and theta for these objects. Another information that we have, the velocity for this color has a constant value as a 4 feet per second. We can resolve the velocity along the X and Y. If I resolve it, this is the velocity for the X component will be V cosine 60. This is the X component of the velocity, and the Y component of the velocity is V sine 60. The value will be 2 feet per second, and this is 3.46 feet per second. Let me draw it again, okay? This is X, this is Y. This is the vector of the velocity along the X component as a 2 feet per second. And this is the vector of the velocity along the Y component, that is 3.46. Why I'm doing this one? Because we should find the velocity in the polar coordinate system. Okay, first I resolve the velocity along the X and Y components, then we convert or bring or transfer to the polar coordinate system. And this is the setup of the polar coordinate system for this problem. This is radial component as a positive direction. This is negative. This is positive for theta, and this is the negative for theta. But what is the angles between the x-axis and the radial component? How we can find? If you look at the problems, we have information about the location of the point A or color A. Now we can find these angles, okay, based on these two information. Again, we cannot use 60 degree, okay, because for polar coordinate system, everything is start from origin and then reach to the objects, okay? For this reason, these angles, if I show by theta, the theta is not equal to the 60 degree. Okay, for finding the theta, we have the inverse of the tangent of y over x. What is the value of the y? For position of the polar A, 1.9 over 2.3. And theta becomes 39.6 degrees. Is meaning these angles 39.6. Now we start to resolving these vector along the polar coordinate system. Okay. This is next to the angle is a 2 cosine 39.6. How about this component? Now we use the cosine. This component become as a sine. 2 sine 39.6. Now we can say for vector of the 2 feet per second, the polar component will be 2 cosine 39.6 ER and is a positive direction. How about the theta components? In the negative directions. For this one, we have negative 2 sine 39.6 E theta. Exactly, we do all of these steps for the velocity along the y component. This is as a 3.46. We can say these angles is 39.6. This is one component. This is another component of this vector. We have 39.6 cosine, sorry, 3.46. Cosine theta, and this is in the positive direction of the theta. And this is another component, 3.46 sine 6. And this is in the positive direction of the radial components. Now we can find the total velocity for these two vectors that we have already resolved along the r and theta. This is the r component and this is as a theta component. The value of the velocity will be cosine 39.6 And the value of the velocity will be 3.1.4 e theta plus 3.75 e. This is the vector of the velocity in polar coordinate system. This is the answer of the part A. For part B, we should find the omega. Okay. If you remember, for the velocity in the polar coordinate system, the radial components, okay, is involving with the omega, okay, and for this reason, we are using the theta component of the velocity. V theta is found based on R times theta dot. Okay. The value of the V theta based on the answer of the part A is a 1.4 feet per second. What is the value of the R? Okay, the value of the R is determined by the R is the distance of the origin to the color A. If you look at the problems, the coordinates of the point A is given as a 2.3 and the y as a 1.9. For this reason, the value of the R will be x squared plus y squared. And this value is follow this equation. Now we are plugging to the equation of the theta component of the velocity. And the value of the theta, once we solve this one, the theta dot or omega or derivative of the theta respect to the time will be 0.468 radian per second. This is the answer of the part B. This is the this video is some examples related to the polar coordinate system. As you can see in these few examples, for setup of the polar coordinate system, always we should, for the radial component, should solve from origin, reach, for example, if we have an object here, reach to the object and continue. This side outward from the origin always as a positive direction for radial components, and this is about negative area. How about the theta? It's depend on the rotation of the object. For example, if the figure or if the problems is mentioned, theta is increasing in this way, this is the positive direction for the theta. And how we can draw the transverse components? Okay, it's a perpendicular to the R. For example, once the theta increasing in this way, this is the positive direction for theta, and this is the negative direction for theta. This is about the examples once the theta increasing the clockwise. But once the theta increasing the counterclockwise, for example, the figure show or the problem show the theta increasing in this way. The radial component, same as this one. This is the positive direction. This is the negative directions. But how about the theta? The direction is changing. This direction become positive direction for theta, and this is the negative direction for theta. And another point that we have to know that for polar coordinate system against and the anti-coordinate system, the velocity in polar coordinate system has two components. But for anti-coordinate system, the velocity just has one component along the t-axis or tangential component. This is the end of this video. Thanks for watching.